In this video, we will discuss a common technique for regularization which is referred to as penalty-based regularization. Penalty-based regularization is a common technique not just in neural network learning but also in all types of machine learning algorithms. In order to motivate penalty-based regularization, we will revisit an example that we discussed in a previous lecture. In this case, we have the problem of linear regression. Here we have a single independent variable x and a single dependent variable y. And the problem is that given training pairs x, y, we want to predict y from x. In this case, the y is modeled as a polynomial function of x. Now obviously we have various choices of this polynomial function. For example, we could choose a fourth order polynomial such as y is equal to w0 plus w1x plus w2x squared plus w3x cubed plus w4x to the power 4. Or we could choose a linear model which is simply y is equal to w0 plus w1x. Now in this particular case, since the shape of the data distribution is somewhat nonlinear, the first impression would be that the use of a polynomial model should be better than the linear model. However, as we discussed in the previous lecture, when the amount of data is limited, one generally does better with linear models because the linear models have lower variance with the choice of the training data. So what does this really mean in terms of economy in parameters? As you will note, the linear model uses only two parameters, w0 and w1, whereas the polynomial model uses 5 parameters. What this means is that a lower order model has economy in parameters. And economy in parameters generally discourages overfitting. One way in which one could have economy in parameters in the case of neural networks is to choose a neural network with fewer units per layer. Doing so enforces economy and reduces the level of overfitting. However, the problem is that when you reduce the size of your neural network, you also reduce the power of your model. So here what your main problem is that when you fix the architecture upfront, what you have is an inflexible solution. Now, an alternative solution, which is a softer solution, is to use a larger model but impose a tunable penalty on the parameter use. So instead of restricting the number of parameters you are using upfront, you add a penalty on using these parameters to your loss function. So imagine that you have the same polynomial regression model where y is given by wi x to the power I, and you sum it from I from 0 to d. And in this case, your loss function is essentially the squared loss over the training examples, which is the first term. And then you add this L2 regularization term, which is essentially lambda. Lambda is your regularization parameter. It decides how much regularization you want to use. So lambda is always positive, and when you use larger values of lambda, you're using more regularization. You're increasing the bias of the model and reducing the variance of the model. And then wi square. So what this will encourage, it will encourage the values of wi to be small. So this is a soft way of feature selection. Rather than saying upfront that we want to set some of the values of wi to be 0 and choosing a lower order model, you are essentially saying that, okay, I'm going to impose a certain level of penalty and I'll let the model decide which parameters are important. And the key point here is that you can, of course, tune the value of lambda using a validation set. And what one has generally seen in neural networks, because you can also apply this type of regularization in neural networks, is that using a softer approach with a more complex model tends to perform better. So what is the effect of the updates? Now we can, given the modified loss function in the previous slide, we can work out the details of the updates. So when you work out the details of the updates, the main effect of the regulation parameter lambda is this additional term that you first multiply. First you contract wi by multiplying it with a value less than 1. So this value is 1 minus alpha lambda. 1 minus alpha lambda. Typically the values of alpha and lambda are chosen in such a way that 1 minus alpha lambda is between 0 and 1. So obviously if you choose larger values of lambda, you are contracting the value of wi more. So, and then of course the second term is simply the loss based update. So this actually has a neat biological interpretation. You can interpret this type of update as decay based forgetting. So the idea is that over time during the training, unless the loss function tells you to increase the value of wi, left to its own devices, the value of wi, the absolute value of wi will always grow smaller and smaller. So unless a parameter is important, it will have small absolute value, and what you're doing is that you're giving the model the flexibility to decide what is important, and especially because you tune lambda, the model has even more flexibility in deciding what level of complexity to use by choosing an appropriate value of lambda, and this is better than inflexibly deciding upfront. Now, from the perspective of the backpropagation updates, the main difference to the backpropagation updates is that you perform the same updates, except that now you also multiply them by this contractive parameters. Now, there are also some enhancements that one can do, is that the parameters in different layers, they are updated at different rates, but for now we'll just work with this simple solution. Now, the previous case, I discussed L2 regulation. Why do I call that L2 regulation? So when you look at this penalty, it's wi square. So you're adding the sum of the squares of the parameters. That's like the L2 norm of the parameter vector. You can also penalize the L1 norm of the parameter vector, which is basically the absolute value of wi. And in this case, again, the loss function is a similar form, and the update actually has slightly different form. Instead of multiplying it by a contractive value, you are essentially reducing it by a certain value. So this is essentially wi minus alpha lambda si minus alpha, and the second term is always the derivative with respect to the loss function, which you compute during backpropagation. Now this value of si is minus 1 when wi is less than 0, and it's plus 1 when wi is greater than 0. So what does this mean? So if your parameter wi is positive, its absolute value will be reduced, because what is going to happen is that si will be positive, alpha and lambda we know are positive, so you'll be subtracting a positive amount from a positive value. If the value of wi is negative, what is going to happen is that you will be adding a small positive amount to it, because si will be minus 1 in that case. So in both cases you are reducing the absolute value, except that in this case the change is additive rather than multiplicative. Now, one question is, which one is preferable? Is L1 regulation preferable, or is L2 regulation preferable? So L1 regulation has a certain property that it leads to sparse parameter learning. So what it means is that many of the weights in the neural network, they become zero at the end of training, and these zero values of wi, they have no effect on the model because no activations flow through them, and they can simply be dropped. So what this means is that your neural network has fewer edges, and you have regularized your neural network by having fewer, by having a smaller complexity. This kind of idea, there is actually a paper called Optimal Brain Damage, where they actually discuss how you can perform this kind of dropping out of edges from the neural network in order to perform regulation. Now, L1 regulation, the main reason it is preferred is because of its sparse solutions, it often gives you good interpretability. However, when you're talking purely about performance, L2 regulation generally provides better performance, and in fact, it's the preferred solution in most real settings. Now, regularization has a very interesting connection with noise injection. So, the connection is that performing L2 regulation with parameter lambda, it's equivalent to adding a Gaussian noise with various lambda to the input. So, you don't change the output, just the input features, you add Gaussian noise with variance lambda to each feature. Now, what is the intuition for this? The intuition for this is that when you add noise to the different features, remember that when you're talking about linear regression, so let's just talk about linear regression where you just multiply the feature values with the coefficients. What's going to happen is that when the absolute values of your coefficients are large, the bad effect of noise will be larger. So the bad effect of noise will generally be minimized with simpler models when you have smaller absolute values of the parameters. And the formal proof of this result is in the book. Right now I'm only providing the intuition. Now, this result, of course, is only true for a single layer network, that's linear regression, but the main value of this result is for providing the general intuition. And you can actually show similar results for denoising autoencoders. You can show that adding a small amount of Gaussian noise is equivalent to performing L2 regularized singular value decomposition. Now, one can also penalize hidden units. Here we have just talked about weight regularization. Penalizing hidden units has other applications, especially in unsupervised settings. When you're using autoencoders, you can apply L1 penalty. So you can have an autoencoder which is over-complete, in which the hidden layer has more number of units as compared to the number of inputs, and then you can apply an L1 penalty on the hidden layer. And what happens is that this type of model, you can train it using a straightforward modification of backpropagation. All that you'll have to do is that the penalty contribution of the hidden units are picked up during the backward phase, and in fact the details are discussed in the book. There's also other ways in which you can perform regulation. One is a very important way is what is called hard and soft weight sharing. Now, hard weight sharing actually is used at several places. So, for example, in autoencoder, you often tie the weights between the encoder and the decoder. Similarly, in a recurrent neural network, because at each timestamp you're building an identical model, what you do is that you have a time-layered network in which the weights in different time layers, they are shared. So often this type of fixing certain weights in your neural network to be the same is a form of regulation, and it's done using domain-specific insights. So if you know something about your specific domain, you can use this type of approach. And how you handle shared weights, I will not go through here because it's discussed in the lecture on backpropagation. Finally, hard weight sharing is not the only way to perform regulation. There's also an approach called soft weight sharing. So suppose you have some insight that two weights in your neural network, they ought to be similar, but you don't want to impose the hard constraint that these two weights have to be exactly the same. So what you can do is that you can add a penalty lambda wi minus wj whole square by 2 to the loss function, where wi and wj are the weights of those two edges. And what's going to happen is that when you work out the details of backpropagation and you add the effect of the soft weight sharing, the update to wi will include this extra term alpha lambda wj minus wi, and the update to wj will include this extra term alpha lambda wi minus wj. The effect of these extra terms is that it will tend to pull the weights closer to one another, and how aggressively it's going to do the pulling is going to depend on how large a value of lambda you pick. That's your regularization parameter. In general, hard weight sharing is more common than soft weight sharing, and we will discuss several examples of this in later lectures.